Hello students, welcome. In last video, we have discussed about the rate, average rate as well as the instantaneous rate of a chemical reaction. Today, we will learn about a graphical representation of instantaneous rate of reaction and one example to explain the instantaneous rate. Okay? A graphical representation. A graphical representation of instantaneous rate. Instantaneous rate means the infinitesimally small change in a concentration of any species divided by infinitesimally a small change in a time. Okay. When we plot a graph of a concentration of a reactant versus a time, the graph will be like that. Suppose on x-axis there is a time, on y-axis there is a concentration of a reactant species in. Okay, suppose A gives product B is our reaction. Initially, the concentration of reactant is very high. Suppose this is the initial concentration of reactant. At time t is equal to 0, the concentration of product is also equal to 0. We know that as reaction proceeds, the concentration of reactant goes on decreasing and we will obtain such kind of a curve. Okay? That is, with increase in the time, the concentration of reactant goes on decreasing. If we draw or if we plot such time, it will give you a slope of a curve. Again, a slope is nothing but small decrease in concentration of reactant A with a small change in time interval. That is minus their concentration of reactant divided by del T is equal to a slope of a curve. This is the graphical representation of instantaneous rate when we plot the graph of the concentration of reactant versus the concentration of product. If we plot another graph in which the concentration of a product is plotted against initially when time is equal to 0, the concentration of product is also equal to 0. Suppose when a reaction proceeds, the concentration of this product goes on increasing and we will obtain a such kind of curve. Here, the slope of product is equal to del P upon del T. That is the increase in the concentration, change in concentration of product with respect to small change in del T. And the instantaneous rate of this reaction is equal to minus del concentration of P upon del T, which is equal to del change in concentration of P divided by del T, which is equal to instantaneous rate of reaction. This is the graphical representation of instantaneous rate of reaction. Okay? Now, the instantaneous rate can be explained with the help of one a reaction. That is, consider the reaction between a nitrogen gas reacts with a thrice hydrogen gas to give 2 moles of ammonia NH3 in the gas system. That is the reaction in which 1 mole of nitrogen gas reacts with 3 mole of hydrogen gas to form 2 moles of ammonia. That is, here the coefficient of reactants as well as the products are different. And for such reaction, the instantaneous rate of a consumption of nitrogen is equal to minus small change in concentration of nitrogen del N2 divided by del V. Okay. Now, similarly, the instantaneous rate of consumption of another reactor, that is hydrogen, if the gaseous state is equal to minus, a minus I can indicate that concentration of reactor goes on decreasing, minus 1 upon its coefficient 3 into small change in concentration of hydrogen divided by small change in the time taken. Now, the instantaneous rate of a formation of ammonia in a gaseous state is equal to plus 1 upon its coefficient del concentration of ammonia divided by small change in time del T. Okay, these are the rate of reaction with respect to a reactor nitrogen, hydrogen and products ammonia. The instantaneous rate of overall reaction is equal to the rate of reaction is equal to minus del concentration of nitrogen divided by del is equal to minus 1/3 the concentration of hydrogen divided by dT is equal to plus 1/2 concentration of ammonia divided by dT. This equation gives the rate of overall reaction. After a number of experiments or number of calculations, it is observed that the rate constant values for all consumption as well as products remain the same. That is, any one calculation gives the overall rate of reaction. Okay, with the help of one problem, we can prove that the calculation of any one instantaneous rate, either the reactants or products, gives the overall rate of a reaction. Show that the rate of reaction is same whether a rate of reaction is expressed in terms of a consumption of any reactant or any product. We have to show that the rate of reaction for this given reaction is same for the rate of consumption of these reactants or the rate of formation of these two products. We have to prove it. The reaction is twice N2O5 gas gives 4 moles of nitrogen dioxide plus 1 mole of oxygen gas. Here, the concentration of reactants and different products are given at different time intervals. This is the chart of table which indicates, which shows the concentration of reactant and both products at the different time intervals. Suppose observation number 1, when time is equal to 0 seconds, that is initially, the concentration of reactant is equal to 0.3 moles. At 0 time, before starting of an reaction decomposition, the concentration of product is equal to 0 moles and 0 moles. Second number of observation. After 200 seconds, when the time is equal to 200 seconds, the concentration of reactant goes on increasing from 0.03 to 0.021. That is concentration increases. The concentration of N2 becomes 0.017 moles, which is 0 at 0 time interval. The concentration of oxygen becomes 0.00435 and so on. This is third and this is the fourth. By using this data, we can prove that the rate of consumption of any reactant or the rate of formation of any product will be same. Okay. First of all, the rate of consumption of N2O5 is equal to, according to instantaneous rate, the rate of consumption of N2O5 is equal to minus 1 into del small change in concentration of N2O5 divided by small change in del. Okay. From this table, we can put the values of concentration. Yes, which is equal to minus 1 into del N2O5, that is change in concentration. Change in concentration of N2O5 minus 1 change in concentration 0.0152 minus 0.0213. After subtraction, this value becomes minus 0.064 divided by change in time 1. Here is the multiplication. Minus minus sign becomes plus, that is 1/2. This division is equal to 3.05 into 10 raised to minus 1. Hence, the value becomes like that. 3.05 upon 2 is equal to 1.525 into 10 raised to minus 5 moles per second. This is the rate of consumption of N2O5. We can write this rate of consumption of N2O5 is equal to 1.525 into 10 raised to minus 5 moles per second. We can calculate these values, that is the rate of consumption. Instead of a rate of consumption, we can also calculate the rate of formation. Rate of formation of NO2 is equal to plus 1 upon its coefficient into change in concentration of NO2 divided by change in time delta. Okay, which is equal to 1 upon 4 into change in concentration of NO2. Final concentration 0.0296 minus 0.0174 divided by 200. After solving, after subtraction of these two values and division by 200 into 1 upon 4, these values ultimately comes like 1.25 into 10 raised to minus 5 moles per second. Similarly, the rate of formation of oxygen O2 is equal to, as there is no coefficient, equation or rate of formation of oxygen is equal to plus del concentration, change in concentration of oxygen, which is equal to final concentration 0.074 minus 0.00435 divided by 200. This value is also equal to 1.25 into 10 raised to minus 5 moles per second. Okay? It is observed that the rate of consumption of N2O5, the rate of formation of nitrogen dioxide, as well as the rate of formation of oxygen, all these values are constant. And these constant values prove that from this constant value, we can say that, or it is proved that a rate of reaction is same whether the rate of reaction is expressed in terms of consumption of any one reactant or the rate of formation of product. Okay, importance of chemical kinetics is a rate law or a differential rate law. We know about the law of mass action or law of active mass. What is the law of action or law of active mass? The rate of any chemical reaction is always proportional to the active masses, that is the concentration of a reacting species present in given chemical reaction. Then, according to this law of active mass or law of mass action, the rate of every chemical reaction is directly proportional to the concentration of reacting species. As concentration increases, the rate of reaction can be also increases and vice versa. Now, this rate law or differential rate law or differential rate law can be stated that it is an experimentally determined mathematical equation. It is an experimentally determined mathematical equation which expresses that the rate of chemical reaction in terms of a concentration of reaction which influences or which affects the rate of given chemical reaction is known as a rate law, a differential rate law equation. Experimentally determined, a mathematical equation which gives a relationship between the concentration of reactant as well as the rate of reaction. For this purpose, consider a general chemical reaction AA plus BB gives product CC plus DD. Here A, B, C and D are the coefficients of concentration as well as the coefficients of the product. Okay? Here, the rate of chemical reaction rate is directly proportional to this the concentration of A and also concentration of B. A, B are the coefficients. If we remove this proportionality sign, the rate is equal to a proportionality constant K into concentration of A into a concentration of B. Here, this concentration term are raised to a proper power like X and Y. This is the rate law equation, where K is a proportionality constant called as a rate constant. K is a proportionality constant known as a rate constant. This is the rate law equation. This rate constant, capital K, is independent on the concentration of reacting species. See once again, the rate of chemical reaction is proportional to concentration of reacting species, but this rate constant does not depends upon the concentration of a reacting species. It depends upon a temperature at which a reaction is carried out. The temperature at which a reaction is carried out. To explain this, consider a simple reaction. The rate for a given different chemical reaction. The first reaction in which hydrogen gas reacts with iodine gas to form twice hydrogen iodide. By applying a rate law, the rate of equation will be obtained like that. A rate constant multiplied by concentration of hydrogen into concentration of iodine. That is X and Y both are equal to 1 in this reaction. K concentration A raised to X and B raised to Y, here X and Y is equal to 1. Then second reaction, twice H2O gas gives twice water molecule as well as oxygen molecule. The rate of this given reaction is equal to rate is equal to K into concentration of H2O2 hydrogen peroxide. In third reaction, NO2 gas plus carbon monoxide gas gives nitric oxide NO gas plus CO2 carbon dioxide in the gas state. The rate of this chemical reaction is equal to a rate constant multiplied by concentration of NO2 square nitrogen dioxide square. Okay. This all equation proves that a rate constant is independent on the concentration. In this video, we have discussed up to instantaneous rate, its graphical representation. One problem to prove that either a rate of consumption of any reactor or rate of consumption or formation of product both are similar, and an important subject that is a rate of differential. Okay, now we will stop here. Thank you very much.